Welcome everyone to another amazing installment of the Flipped Classroom, where this time we will be studying impulse and momentum. And today we're simply going to start with just impulse. Now, if we take Math Rep 2 from the beginning of the year and replace A with F over M, since F equals MA, and then multiply through every term by mass, we have mv final on the left side equals mv initial plus F delta T. And if we rearrange it so it looks pretty, we're left with F delta T equals mv final minus mv initial. This is defined as impulse. It is boxed because you can feel free to put it on your card, and simply impulse is defined as change in momentum. Momentum is simply mass in motion, or P equals mv. Don't ask me why momentum is the letter P. It has something to do with the Latin P-E-T-E-R-E, but I have no idea after that. But P is momentum. It equals mv. It's boxed because you can put it on your card. And as you can see above, impulse is change in momentum, where change implies final minus initial. So on the right side of the equation, you actually have final momentum minus initial momentum. Now, impulse itself, when you're solving for it, it could be simply using the left side of the equation as F delta T. Sometimes you may only use the right side of the equation, which is mv final minus mv initial. And sometimes you have to use both sides of the equation. But it's important to note for just a second that both sides have to have the same units. On the left side, force is a Newton times time is seconds, and on the right, the units for momentum are simply mass times velocity, or kilogram meter per second. Now, a Newton is a kilogram meter per second squared, and if we multiply that by seconds, we're left with both sides of the equation as kilogram meter per second. So when writing units, please feel free to use either kilogram meter per second or Newton seconds. Best thing to do now is to start with a sample problem, and feel free to pause this amazing video at any time. But we'll start with something simple. A 5 gram ping pong ball is traveling to the right at 6 meters per second when it is hit with a paddle, and the ball is returned at a speed of 8 meters per second. If the ball is in contact for 0.12 seconds, what is the force of the paddle on the ball? Now, one of the most important things you have to do here is really visualize, and I would suggest drawing a picture, labeling velocities, and especially remembering which way is positive. So we start with our ball moving to the right at 6 meters per second, and it's the initial conditions. The final conditions are the ball moving to the left at 8 meters per second. Notice that it has been labeled as negative 8 meters per second because I've defined to the right as positive. Now the math is pretty straightforward. We have our new math rep, F delta T equals mv final minus mv initial. And when we substitute in all our numbers, the only thing we don't know is the force. So solving for force, we get negative 0.58 newtons. This is pretty straightforward, and it should make sense that the force is to the left because the ping pong ball is traveling to the right and is then hit to the left, so it makes sense to get a negative force. Now on to the next problem, another straightforward one. A pitcher throws a 142 gram baseball, initially at rest, to an unknown final velocity. The ball is released horizontally, and that will come into play later. But the pitcher applies a force of 50 newtons for a time of 0.12 seconds. And what is the velocity of the ball when it leaves the pitcher's hand? Again, feel free to pause the video to write this down at any point. Again, I would suggest drawing a picture of initial and final conditions. So here we have the ball initially at rest. The final, we don't know, but it's moving to the right at some unknown final velocity. Please watch out for words like grams. You have to convert to kilograms. So just plugging into our simple new math rep, you get F delta T equals mv final minus mv initial. Substituting in our numbers, the only thing we don't know is Vf. Solving for Vf, we get that the final velocity is 42.25 meters per second. Now, please be aware that one of the best parts of impulse and momentum is its ability to connect with previous topics. So, for example, a follow-up question could be, if the ball is released from a height of 2 meters, how far will it travel before it hits the ground? This is horizontal projectile motion, and if you feel like pausing the video and giving it a shot, I would remind you to draw a table. This is horizontal, so the initial velocity in the y-axis is 0, but give it a shot and see what happens. You probably didn't pause the video, but hopefully you did. If you did it properly, your answer for delta dx should have been 27.04 meters. One last problem just to show how it connects to previous topics. We have a 10 kilogram block sliding down a frictionless 8 meter long incline angled at 15 degrees. And once the block reaches the bottom, it skids to a stop along a horizontal surface, and it only takes 3 seconds to stop. The question is asking you for the coefficient of friction between the horizontal surface and the block. Again, pause the video if you want to write this down. I would again start with a picture. Here we have our incline, 8 meters long, angle 15 degrees, initial velocity is 0. At the bottom of any two-part problem, please remember that the final velocity for part 1 becomes the initial velocity for part 2, in which the block skids for a time of 3 seconds and comes to a stop. I've added here the labeling of the positive direction, which I should have done in the previous problems, but it's sometimes useful to remind yourself the direction, in this case, the direction in which the object is moving, is the positive direction. So the beginning, the first part, is simply an incline, and the second part is the impulse, the change in momentum. Setting both sides up for part 1 on the incline, we have initially potential energy, and it's not moving, and at the bottom there's no more potential energy left, so we have kinetic energy. And for the impulse part, we have F delta t equals mv final minus mv initial as usual. If we substitute in our math, on the left side we have mgh equals 1f mvf squared, and for the impulse we have the force of friction acting for some time. And just a little hint, it may help you to draw an FBD to remind you that the force of friction is to the left, which we've defined as negative, and that's going to be mu times the normal, and on a horizontal surface, the normal force is simply mg. So you are left with negative mu mg, delta t equals mv final minus mv initial, and the mass actually divides out of all the terms, which is kind of convenient. Substituting in some numbers, for part 1, we get, the only thing we don't know is the final velocity squared. So solving for final velocity, we get 6.37 meters per second. This can be substituted then all the way on the right side of the equation here, so that VF becomes VI for the next part. And we are left with only one unknown, which is mu. So solving for mu, you get 0.22. Now, in summary, impulse is simply defined as a change in momentum. And remember, when you hear change in momentum, that's usually the right side of the equation, literally mv final minus mv initial, but sometimes you can use the left side of the equation as well, or both when solving a major problem. Momentum is simply mass in motion. It's m times v. Don't make it more complicated than it is. This is our new math rep for impulse, and it helps to draw pictures so you can focus on the initial and final conditions and help set up the problems. It also helps to label the positive direction, since the most common math error when doing these problems is positive and negative direction. Please remember that impulse and momentum connect to previous topics, so be prepared for multi-part problems where the final velocity from one part becomes the initial velocity for the next part. Now, if you're inspired, feel free to start the 5 problems that are basic impulse problems. Some of them do connect to previous topics. Otherwise, we will be working on these problems tomorrow in class.